Hello everyone, my name is Jiawei Guo. I'm from Science and Technology Research Institute for Decarbonization in National Taiwan University. Today I want to talk about the carbon storage. I will focus on fundamental processes and physical behavior of CO2 storage in deep saline aquifer. So, what's the motivation of carbon storage? Because we want to avoid dangerous climate change. Because human activities, CO2 emissions have risen dramatically over the past 200 years. Before 1950, CO2 concentration in the atmosphere is below 300 ppm, but right now we're already in the 422 ppm this year. These high CO2 emissions leads to the buildup of CO2 concentration in the atmosphere, which results in global warming, extreme weather events, and people are suffering. If we want to avoid these climate catastrophes, such as super droughts, rising seas, mass extinction, acidifying oceans, and heat waves, we have to limit global mean temperature to 2 degrees C since pre-industrial level. Unfortunately, we already hit 1.5 degrees C this year. This is the figure shows that global greenhouse gas emissions and warming scenarios. You can see if we use the current policies, the temperature can still up to 3 degrees C at the end of the century. If we want to go to 1.5 degrees C pathways, we have to cut greenhouse gas emissions in half by 2030 and reach net zero CO2 emission by mid-century. This is a huge gap we need to achieve. So how can we achieve this ambitious goal? We can increase energy conservation and energy efficiency to reduce energy intensity and energy demand. We can reduce carbon intensity and emissions. For example, instead of using coal, we switch to natural gas to generate electricity. We can increase percentage of renewables, maybe use nuclear energy, but with our carbon capture and storage, net zero is practically impossible. So CCS could make a large contribution to reduce CO2 emission. But what is actually carbon dioxide capture and storage? The basic concept of CCS is shown in this figure. This is a stationary power plant. We capture CO2 before it released to the atmosphere. We do the compression of the captured CO2 and use pipeline transport CO2 to the potential injection sites. Finally, we inject CO2 at 1 kilometer or deeper into rocks with tiny pore space. At these steps, CO2 behave as a supercritical fluid. So it will have gas properties but with a density like that of a liquid. So we can store more CO2 in the pore space. We have different options for geological sequestration. Here we only focus on deep saline formations because it has a large storage capacity. It's worldwide distributed and we can immediately accessible to store CO2 in the deep underground formations. This is the typical CO2 storage in saline aquifer. We have seals on the top of the reservoir. This low permeability of rocks can prevent CO2 moves upward. The system is dealing with the supercritical phase of CO2 and brine, so it's a multi-phase flow problem. The typical distribution of CO2 plume is shown here. You can see the plume can be divided into 3 different flow regions based on the 2 transition points. In the near well region, injection rate is large. The viscous force is dominated here. When CO2 moves forward, gravity force becomes important. In the front of CO2 plume, the CO2 flow velocity is so slow that capillary force is dominating in this region. So during the injection, CO2 plume is governed by viscous force, gravity force, and capillary force. And we can use dimensionless numbers to compare the magnitude of these physical forces. And we can characterize flow regions based on the 2 transition points. So it's important to characterize this different flow region because it's very useful for upscaling. The keywords I want you to remember, we have viscous force, viscous dominating region, gravity dominating region, capillary dominating region. We have two transition points to characterize these different regions, and we can use dimensionless number to study the scaling from one system to another, and this is a multi-phase flow system. The other important factor to affect the physical behavior of CO2 plume is rock heterogeneity, because rock properties vary spatially, so the rock heterogeneity is very common in geological formation and exists at every scale. Therefore, it's important and realistic to include heterogeneity in multi-phase flow system. We can expect that these different scales of heterogeneity, from pore scale to core scale, and to the borehole scale, and finally to the plume or field scale. These different scales of heterogeneity will result in complexity when solving multi-phase flow problems. The first key issue of CCS is how CO2 plume migrate, what is the migration rate, and how far of the migration. To answer this question, we have to study multi-phase flow theory. The physical mechanism behind the CO2 plume migration depends on the complex interplay of these following factors, including three physical forces, which are viscous force, buoyancy force, and capillary force, heterogeneity, structure, and the reservoir and flow properties. So all these different factors can affect CO2 plume migration.